Hello, welcome to another module of this course, Analog Circuits. So, in the previous modules, we have never come across what we called nonlinear circuits. All the circuits we have discussed so far, including the Butterworth filters, the Chebyshev filters, they all belong to a category called linear circuits because they follow the principle of linearity. Even Opamps, as we were discussing initially, they are linear circuits, but I mean Opamp as used for a simple summing amplifier, for amplification in general, Opamps act as linear circuits. But the use of Opamps is not just limited to linear circuits. There are some specific nonlinear circuits which can also be designed using Opamps, using the various properties that an Opamp has. And these nonlinear circuits have a number of applications, as we shall see later. So, let us start with some nonlinear applications of Opamps. So, when I say nonlinear application, it is those circuits which any circuit which does not or do not follow the linearity principle is a nonlinear circuit. So, recall again once again what is the linearity principle. First is that the output should be proportional to the input. Output, so these are the two main linearity properties which strict linear systems have: output proportional to input, and the second is principle of superposition is valid. So, any circuit which does not follow any one of these two principles is a nonlinear circuit. Now, since linearity is easily defined, nonlinearity, as I said, any circuit that does not follow the linearity principle. So, that implies that there can be lots of nonlinear circuits. So, we shall discuss some specific ones that are useful for practical applications, and one such circuit is what is known as a limiter. So, limiter is the circuit that does not allow, suppose this is my V I and this is my V O. So, V I is the input voltage and V O is say the output voltage. A limiter is a circuit that will not allow the output to go on increasing at a constant rate. So, ideally a limiter should be like this. Similarly, on the negative side also, if I extend my axis on the negative side also, beyond a particular negative voltage V I, some value say L or say let us call it V I dash and V I double dash, it will again for an ideal limiter, it will not allow the output voltage to go any further down. So, that is an ideal limiter, but suppose instead of such a strict cutoff, I have a circuit where instead of the output becoming flat after a certain input voltage, say V I double dash, say if the slope also changes abruptly, whereas originally it was supposed to go like this, but after this voltage input voltage V I double dash, the output follows a different slope, and in this case also say the output follows a different slope, then that circuit is also called a limiter. So, how do we design a limiter? Now, there are many circuits for limiter. We shall discuss two of them. So, let me first draw the limiter circuit and then try to explain its properties. So, this is the circuit. Why am I saying that this is a limiter? First of all, note that there are two diodes here. Now, we will discuss about the properties of a diode a little later, but for now you can take it that a diode is a device that allows current to pass through it in only one direction. So, if this is a diode, then a minimum voltage called the threshold voltage. So, this Vd is known as threshold. This has to be supplied across the terminals of the diode in order to make it conduct. Similarly, for this diode D2 also, in order to make it conduct, now this triangle points to the direction in which the diode allows current through it. So, in this diode, current will pass only from this terminal to the this terminal, and also for this diode to conduct, minimum voltage Vd has to be applied. Okay. Now, so as I said, a diode is a device that allows current to pass in only one direction. So, in this case, of course, a diode has some minimum internal resistance also, but for that is a very small resistance, and for this particular circuit we shall ignore it. Now, if this diode is conducting in one direction and if the internal resistance of the diode is very small, then we can simply assume that this is a short between this terminal to this terminal. So, if this diode is conducting, then there is a short existing between this terminal and this terminal. Let us say the voltage at this terminal is called VA and the voltage at this terminal is called VB. Now, this terminal is at virtual short with the other, with the non-inverting terminal. Hence, and since the non-inverting terminal is grounded, therefore, this terminal will also have a voltage of 0 voltage. So, if VA is lesser or equal to minus Vd, then this diode D1 will conduct. Similarly, if Vb is greater or equal to Vd, then this diode will conduct. If VA is lesser than minus Vd, therefore, this diode will conduct, and so this resistance R3 will then be in shunt with Rf. Similarly, if D2 conducts, that is, if Vb is greater than Vd, then R4 will be in shunt with Rf. Okay. Now, it can be shown that both D1 and D2 can never be conducting at the same time. Okay. So, let us see now how the voltage VA and VB change. Also remember that when D1 or D2 are not conducting, suppose D1 is not conducting, then there is an open between this terminal and this terminal. If there is an open between this terminal and VA, so that means the total resistance appearing across this point and this point is Rf. If D1 is conducting, then the total resistance between this point and this point is Rf in shunt with R3. Similarly, if D2 is conducting, as I said, R4 will be in shunt with Rf, but if D2 is not conducting, then simply Rf will be in shunt between this terminal and this terminal. So, with these in mind, let us try to write some equations. So, suppose initially VA is high and VB is low, and say VO is nearly equal to 0. Okay. D1 and D2 are both off, okay, then V0 will be equal to minus Rf upon R1 Vi, okay, right, isn't it? V0 will be simply equal to Rf upon R1, that is a inverting op amp configuration. Vo will be proportional to Vi, okay. So then how will it look like? If I draw the input output characteristics, how will the input output characteristics look like if both D1 and D2 are off? Okay. Okay. If it will be like this. Now, you see that as Vi becomes larger, my Vo becomes smaller, or rather I should say more negative, till a point where Vo is so less, okay, that if you go back to a circuit for a minute. So, as Vi increases, we see Vo goes on becoming more negative, and as Vo goes on becoming more negative, Va also goes on becoming more negative. So, now what is the relationship between Va and V0? So, this is a simple, see, D1 is off. So, there are two voltages which are influencing the voltage at Va. One is Vo and the other is the supply plus V. So, in order to get an expression for the voltage Va, we can apply the superposition principle, where we first consider the effect of this plus V voltage after shorting Vo, and in the second case we short this terminal and consider the contribution of V0 to Va. So, if we do that, the expression that we get for Va is as follows: Va will be equal to V R3 upon R2 plus R3 plus V0 R2 R2 plus R3. Okay. So, what we have here is this. If let us just consider this part of the circuit only. Okay. So, see, if V plus V voltage is shorted, then the contribution of V0 to Va is R2 divided by R2 upon R3 multiplied by V0, and if V0 is shorted, then the contribution of plus V to Va is R2 R3, I beg your pardon, divided by R2 plus R3 into plus V. So, that is what we have written here. Similarly, we can also write an expression for this part, the lower Vb, and the expression that we will get is, the only difference between Va and Vb is that Vb is influenced by minus V and V0, whereas Va is influenced by plus V and V0. Therefore, proceeding similarly, we can write an expression for Vb as okay. Now, if we go back to the circuit once again, so as VO, Vi increases, my VO becomes more negative, and as we can see from this expression, the more negative VO becomes, the more negative Va also becomes. And there might be a point at which Va becomes so low that this diode starts conducting. Note that this terminal of the diode is connected to 0 volts. So, if Va becomes sufficiently low, that is, if the voltage across the diode crosses the threshold voltage, then this diode starts conducting. Now, what is that voltage? Suppose, so we can say that when Va is equal to minus Vd, the threshold voltage, D1 conducts. Okay. So, then from this expression we can write, from this expression, so I can just draw an arrow, minus Vd is equal to plus V R3 upon R2 plus R3, and let us suppose the value of the output voltage when Va is equal to Vd is equal to is what I call L minus plus L minus R2 upon R2 plus R3. So, if we go back to the graph once again, so what is happening is that at this particular, extend this a bit, there is a certain value of output voltage which I am calling L minus. Okay. At this output voltage, diode starts conducting. Similarly, when Vi becomes more negative, there will be another output voltage value which I am calling L plus, where diode D2 starts conducting. Okay. So, for D2, diode D2, what should be the condition? Let us once again go back to our circuit. When Vi goes on decreasing, then Vo goes on increasing, and as Vo goes on increasing, Vb also goes on increasing, and that is also verified from this equation, isn't it? This is not there. As we can see, as Vo goes on increasing, my Vb will also go on increasing, and there will be a certain value of Vb when the voltage across D2 crosses the threshold voltage and D2 starts conducting. When that voltage is achieved, this diode will start conducting, and that output voltage for which Vb crosses the threshold voltage, I am calling that as L plus, and that is what I have marked in this graph, L plus. So, what is the value of this L plus? How will we determine? We will determine it from this equation. Okay. So, let us plug in the value of Vb in this equation. When Vb is equal to Vd, diode D2 starts conducting. Okay. So, then Vd is equal to minus V upon R4 upon V R4 divided by R4 plus R5 plus, if I call that value of V0 as L plus, R5 upon R4 plus R5. So, we have these two expressions for finding out L plus and L minus, and the value of L plus and L minus that we obtain are as follows. So, L minus is given as minus V R3 upon R2 minus Vd 1 plus R3 upon R2, and L plus is given as plus V R4 upon R5 plus Vd 1 plus R4 upon R5. So, once this happens, that we reach these, when Va reaches L minus, or I should say the Vo reaches L minus or Vo reaches L plus, diodes D1 and D2 start conducting, and if they start conducting, then what happens? As I had mentioned at the beginning, when diode D1 conducts, then the net resistance appearing across the feedback loop is Rf in shunt with R3. Okay. So, then what we get here is that beyond L minus, the slope will change. So, here the slope was minus Rf upon R1, here the slope will be minus Rf in shunt with R3 upon R1, okay, and here the slope will be minus Rf in shunt with R4 upon R1. Okay. Now, see that this L minus and L plus can be adjusted independently. The reason why the limiting action is happening, suppose you are giving a sinusoidal input to the Vi. Okay. So, beyond this point, the output will be clipped. Okay. Any input voltage which exceeds this value will be clipped or will be amplified with a different gain factor. Okay. That is why the limiting action happens. Now, if you make Rf is equal to infinity, if Rf is equal to infinity, then the characteristics becomes something like this. The slope is minus R3 upon R1, and here the slope is minus R4 upon R1. Here the slope is infinity. Okay. In this lecture, we studied one of the two types of limiters that I had mentioned. In the next module, we will be continuing our discussion on limiters and also studying in somewhat detail the properties of a diode. Thank you.